Good afternoon, everyone. My name is ICCM, and I'm a doctoral student at the Department of Industrial and Systems Engineering at Rutgers University. This is one of the studies that we conducted with my advisor, Dr. Melike Baykal-Gürsoy. It's entitled Attacker Behavior Detection in Critical Infrastructure, and it analyzes how attackers behave differently than civilians in an attack location. Lone actor terrorists are individuals that prepare for, plan, and commit the attack by themselves without any hierarchical links to any terrorist organizations. Our previous analyses have led to 4 temporal spectra for lone actor terrorist behavior. Early behavior is about the radicalization process. The preparatory behavior deals with the attack preparations. Incident scene behavior involves counter-surveillance behavior to avoid being detected, and the after-attack behavior refers to the attacker being caught or escaping. Early preparatory and after-attack behavior are generally available after an attack in newspapers and other sources. But the incident scene behavior is generally caught on grainy footage and is not available to public. Also, the attack conditions are impossible to replicate. The 2D game generated at the GRIS lab assists in partially circumventing this obstacle, and we use this 2D game data as a surrogate for incident scene behavior. The Paint Fever game generated at the GRIS lab is designed to mimic critical infrastructures of various layouts. These layouts consist of several rooms and halls with different adjacencies and civilian populations. Here is one of the layouts. This sample critical infrastructure has 9 rooms with varying sizes. Some rooms have entry and exit points to provide in and out flow of pedestrians. Each game comprises game rounds with 2 defenders and an attacker in each round. A player can play as either an attacker or a defender throughout one game. The attacker's objective is to plant a paintball in a room and escape from the infrastructure without them or the paintball being caught. The paintball explodes and paints everyone in that room. The attacker can see nearby rooms and everyone within a specific range. Therefore, if any defenders are in range, the attacker can see them. If the player plays as a defender, the computer plays as the other defender and the attacker. The defender can't see the attacker, and their objective is to catch the defender and the paintball if planted. One of the most important features is centrality, which is the number of adjacent rooms. On this map, room 3 is the most central room with 5 neighbors. At each game round, the defender has different attacker detecting capabilities. These can stem from the security resources allocated to each room. If a room is bright, there is higher visibility and the detection probability is higher. The pedestrian flow continues throughout a game, and this gives a dynamic population to each room that changes every second. At the playthroughs, we discovered 2 types of attackers. The maximum damager fixates on the most crowded central room and takes their time to be able to plant the paintball to this room. Their trajectory is easily distinguishable from the pedestrians because of their counter-surveillance behavior and making sudden moves when encountered with the defenders. The opportunistic attacker, on the other hand, blends in with the pedestrians and plants the paintball anywhere available that is far from the defenders. As a consequence, our study focuses on detecting the opportunistic attacker. Because opportunistic attackers act fast, this classification has to be done in the first 5 seconds of data. To start with, we split the games for training and testing, and for each game in the training and testing sample, we extract all the features for all pedestrians and the attacker. An important challenge is that for one attacker in a game, there are more than 200 pedestrians in each game, so the classification data is highly imbalanced. To avoid the dominance of pedestrians in the classification model, we use k-means clustering for the time series trajectory data for pedestrians. Instead of the pedestrian data, we use pedestrian representatives, which are the cluster centers. Once the data becomes balanced, we apply random forests for time series to pedestrian representative and the attacker data. Then we test the model on the testing games. We have a total of 156 games and 24 is separated for testing. Clustering and classification, we use the layout characteristics that are centrality rank, population rank, and detection probability rank. To distinguish the attacker from the pedestrians, we also add how they distance themselves to the defender and the nearest exit. The training data involves 133 data points for the attacker, so we decrease the number of data points of the pedestrians to that number as well by using k-means clustering over these features. Once we obtain the cluster centers, we use the representatives of pedestrians. To this new data, we apply time series random forests. Important note is each of 100 trees use a random combination of these 6 features. As can be seen from these confusion matrices, the performance of the training data and the performance of predicting the attacker for the testing data are 100%. Since the data is very imbalanced, some of the pedestrians are also classified as attackers, and this is around 30% of the testing data. From these results, we will extend our model to predict also maximum damagers besides opportunistic attackers. We will also convert this into a dynamic model that changes beliefs on the attackers and the pedestrians as the game evolves. Thank you very much for listening to these presentations. I'll be in the Q&A session for any questions you may have.